The Mixing House, the night Napalm turned inward, Pine Bluff Arsenal, 1944. A low vibration moves through the floor. No one reacts. The paddles turn at the bottom of the tanks. Slow, steady, mechanical. Steel against resistance. A rhythm that has been running for hours. The overhead lights cast a yellow glow across the surface of the liquid. It looks thick, heavy, controlled. A worker stands at the rim of the nearest tank, watching the rotation. The liquid stretches as the paddle lifts, then folds back into itself. It has done this all night. It has done this every night. Nothing about it suggests urgency. Nothing about it suggests danger. It is just another shift, 2 hours from ending, and everything inside the building is operating exactly as expected. Most systems like this don't draw attention. They only make sense when you look closer. If you're interested in that, consider subscribing. The paddle turns again. And then the surface changes. At first, it doesn't look like failure. There is no explosion, no structural collapse, no warning sound. Just a brief, almost invisible transition from liquid to ignition. A blue-white flash moves across the surface of the tank. Not upward, not outward. Across. It travels faster than a human can process. A thin layer of vapor catching all at once. For a fraction of a second, there is no sound. Then, a deep contained whoomp. By the time the sound arrives, the tank is already burning. The worker doesn't step back. There isn't time. The fire is no longer just inside the tank. It has reached the rim, then the floor, then everything else. What burned in that building was not a typical fuel. It wasn't something designed to ignite and fade. It was designed to persist, to remain, to attach itself to whatever it touched, and continue burning. The material inside those tanks had been engineered for a specific problem. Gasoline burns quickly. It spreads. It evaporates. For military planners, that wasn't enough. They needed something that stayed where it landed, something that resisted extinction. The solution was simple in concept. Take fuel and remove its ability to behave like one. The worker at the tank had done this before, hundreds of times. The process was familiar. Check the surface. Watch the consistency. Adjust nothing unless something changed. And nothing had changed. The smell in the air, gasoline mixed with something heavier, was constant. It had always been there. The temperature felt normal. The motion of the paddle felt normal. Everything about the environment reinforced a single idea. This is under control. The mixture inside the tank was gasoline thickened into a gel, not by cooling, but chemically. A powdered compound, derived from fatty acids, was added to fuel, heated, stirred. The result was something between liquid and solid, viscous, adhesive. When ignited, it didn't flow away. It clung. It burned at temperatures exceeding 1,000 degrees Celsius. And most importantly, water didn't stop it. Water spread it. The mixing building was not unique. It was part of a larger system, a system designed for output, continuous production, multiple tanks running at once, each one open at the top, each one heated, each one producing the same material. Workers moved between them. Supervisors observed from the floor. Sampling was manual. Everything required proximity, 3 feet from the surface, sometimes closer, and for weeks, nothing had gone wrong. The system wasn't failing. That's what made it dangerous. It was working exactly as designed. The tanks were at the correct temperature. The mixture was forming correctly. The paddles were rotating at the expected speed. There were no alarms, no visible defects. But above the liquid surface, something else was forming. At 150 to 180 degrees Fahrenheit, gasoline doesn't just sit, it evaporates. It releases vapor into the air above it. That vapor doesn't disperse instantly, it accumulates, and within a specific range between roughly 1.4% and 7.6% concentration in air, it becomes ignitable, not unstable, not volatile in appearance, just ready. The problem is, you can't see that threshold. You can't smell the difference. At 1% and at 4%, the air feels the same, but one of those will burn. The workers knew the material burned. They understood that, but understanding something in theory is not the same as experiencing it. The tanks had always been safe before. The process had always completed without incident. Routine does something subtle. It removes doubt, not because the system becomes safer, but because nothing has gone wrong yet. Inside the system, another process was happening, quiet, invisible. The rotating shaft of the paddle moved through a thick, non conductive fluid. Friction, contact, separation. It generated charge, static electricity. At the same time, workers moving across the floor generated their own charge. Clothing against skin, rubber soles on concrete, small amounts, individually insignificant, but in an environment filled with vapor. They didn't need to be large. They just needed to exist. The ignition source wasn't a failure. It wasn't a malfunction. It was a normal byproduct of the system, operating correctly. The spark, when it came, was likely unnoticed. A tiny arc between a hand and a metal surface, between a component and its housing. Less than a fraction of a second, the vapor layer above the tank ignites first. It doesn't explode. It travels across the surface. And then the liquid beneath it catches. The worker sees it, but perception takes time, roughly zero point 0.3 seconds. That is all. By then, the fire has already reached the edge. The gel does not erupt. It spills over the rim, onto the floor, and where it lands, it stays, burning. The floor becomes the fuel path. Each contact point becomes a new source. The fire spreads at walking speed, not fast enough to outrun instantly, but too fast to escape once it surrounds you. Some workers move immediately. They reach the exits. They make it outside. Others hesitate, not because they don't understand danger, but because the situation doesn't match expectation. This isn't how fires are supposed to behave. There is no single point of origin anymore, no clear direction, just a surface that continues to burn. Wherever it touches, the fire crews arrive quickly, minutes. They deploy hoses. They do what they've always done: apply water. And for a moment, it looks like action. Then the pattern changes. The water strikes the burning gel and breaks it apart, scattering it, each fragment still burning, each fragment spreading. The fire doesn't diminish, it multiplies. Inside the building, multiple tanks, hundreds of gallons each, storage drums, fuel lines, everything feeding the same system. The fire isn't localized, it's systemic, an entire process, ignited at once. The system did not fail. It performed exactly as it was built to. The problem was never instability. It was design, an open system, handling a material that required containment, a process that allowed vapor to exist in ignition range continuously, a production model that accepted that condition as normal. No one in that building believed they were unsafe, not because they were careless, but because the system around them implied safety. If it were dangerous, it wouldn't be running. If it were unstable, it would have failed already. That logic held until it didn't. The building burns for hours. Fire crews don't enter. They contain. They wait. The structure consumes itself from the inside. The system, once active, now reduced to heat and residue. The risk had been identified before: vapor ignition, static discharge, open mixing systems. There were alternatives, closed systems, inert gas layers, monitoring. They existed, but implementing them required time. Time meant stopping production, and stopping production was not an option. The process was repaired. The building was rebuilt. The tanks ran again. The paddles turned at the same speed, the same material, at the same temperature. The difference wasn't visible. It rarely is, because the most dangerous systems don't look unstable. They look efficient. They look routine. They look exactly like they did the day before. And sometimes that's the only warning you ever get.